Hi everyone, welcome back. This video is a continuation of what we started in the last one, where we got a quick introduction to the smFISH technique. And if you haven't watched that, I definitely recommend just quickly watching that. It's just a 10-12 minute video, so it's definitely worth your time. Especially if you don't know what smFISH is. And if you do know that, then let's jump into this tutorial where we just go through the process of analyzing a couple of images that we have from the smFISH experiment. Again, smFISH is F stands for fluorescence, right? And that's microscopy based fluorescence imaging, which means we end up with images. And the steps involve counting these spots, and segmenting your nucleus, segmenting your cells, and assigning these spots to the nucleus or outside the nucleus, and so on. So let's walk through a few steps, and especially using the BigFish library, which is amazing. Actually, it provides you all the tools you need for these type of analysis. And again, if you want to be notified of these type of videos for future, this is a great time to pause the video, hit the subscribe button, and of course, while you're there, try to find the thanks button if you're feeling extra generous. Okay, without any delay, let's go ahead and jump into our code. And I'm going to use Google Colab to make sure that all of you have equal access to these type of tools, and we're not going to use anything special. And I'll also provide you a link where you can download, or a process where how you can download a couple of images that we are going to use for this specific exercise. As usual, the code will be shared on my GitHub, and the link is down in the description. Okay, let's jump into the code then. And I'll show you two examples. One where we just have a single plex, meaning like a single example for this single image for our smFISH channel. And the next one, I'm going to show you one where we have like 3 different channels, but no cell, only the nucleus part, because I couldn't get hold of a data set that's got both cellular signatures, so to the point where we can segment the cells. But unfortunately, I only got one where we have nuclei, which is still okay, and the spots within the nuclei itself. But let's start focusing on the first one. And the goal, again, just to reiterate, is to understand various tools that BigFish library actually provides, and perform a few analyses steps using this BigFish library. And bulk of what I show can be found under the documentation of BigFish. So if you really don't like listening to these type of videos or watching these type of videos, you can directly jump onto the BigFish library documentation and get hold of their example files and all that. So I put all of that into a nice one streamlined workflow. So I do appreciate if you can watch this video. Okay, now I put a lot of text because I know I am going to share this file with you. So I'm going to skip reading this and not boring you, by reading that for now. But when it comes to data set and images for this specific exercise, we are going to use these two primarily. There's one called experiment 1 DAPI, experiment 1 smFISH. The DAPI gets used, as you can imagine, to segment nuclei, and smFISH is the channel that contains all the spots that we will be counting. And how do you get hold of these two? Well, you can just run this line, stack dot check input data, by putting input segmentation equals to true. When you do that, you can download the segmented nuclei and cells right there, but it's up to you if you want to put true or false, but we are going to use these two files for now. And what does stack actually mean? Well, if you go down, it's going to be part of BigFish. BigFish.stack as stack, yeah? So that's the part. I should have included that up here, but anyway, yeah, you have the code. So you can run that line. So I did that, and I saved these two images as part of my on my Google Drive. So I'm going to point to those two files. So it's very simple. These are DAPI image and a smFISH image. Okay, we'll look at these images in a second. So that's that. And you can get hold of other data sets by clicking on this. And this PDF actually summarizes a whole bunch of data sets. So go ahead and play with that. And what environment am I working on? Well, first of all, BigFish requires Python 3.6 or newer. And as of mid-June, or actually late June, I should say, 2023, I'm working on Google Colab, and I believe my Python version, we can check our Python version, it's definitely newer than 3.6. I believe it's 3.8. and NumPy and all of these restrictions, all of these requirements, not restrictions, down here. Okay, so with that information, let's go ahead and install BigFish library. And again, it's as simple as pip install MRC BigFish. I'm installing both libraries, MRC and BigFish right there. So it takes only a few seconds, as you can see. And now let's go ahead and start reading the images. And all others, you should already have like NumPy on your Colab. But if you actually install all of this on your local computer, of course, when you create a new environment, make sure you install the NumPy, you install all the others that are mentioned up here. Okay, and let's go ahead and read our import our libraries right here. And the BigFish version I'm using is 0.6.2. And let's import matplotlib for plotting. Of course, BigFish also offers plotting functionality. Of course, it uses matplotlib in the backend, but I'm also importing matplotlib because it gives a bit more freedom for us to do any plots. Okay, so my input path is input, output path is output. Why did I define both? Because from the input, I'm going to read my images, and output is where I would like to save any processed images or any CSV files that I created from my data analysis. So I define my input and output. And now let's, if you want to, again, if you want to download all test images, go ahead and run this. Stack.check input data, path input. So basically it stores the files that you want to download at this specific path. I already have it, I'm pretty sure. So I'm not going to download this. Okay, now let's go ahead and import our images. How do you do that? It's stack.readImage. Okay, stack is, again, I just want to show you bigfish.stack as stack. Okay, so stack.check input data is what we are skipping for now because I've already done that. I downloaded the images. And stack.readImage is my image is located at my input path, and this is the file name for my smFISH channel, and this is the file name for my DAPI channel. Let's read both and print out certain information about these images. And it should be a image of 650 by 500, 23 slices. So this is a Z stack of 650 by 500, 2 channels, right? I'm reading 2 channels separately. You can read them together and then separate them. It's up to you how you want to do it, depending on your input files. But here, we have 2 images, one for RNA, one for DAPI. Okay, from now on, and keep an eye on the D type, unsigned integer 16 here, because some of the functions that are available as part of your BigFish library, they may force you to convert your images to unsigned integer 16 if they're not already unsigned integer 16. So just a quick note, that's why we're printing these, so we know exactly what we're dealing with. Okay, so this is a Z stack, but let's just go ahead and have a quick look at how these images look like. And let's pick a central slice, right? So we have 23 slices, so look at central slice number 11. And let's go ahead and plot both RNA and DAPI images. And again, this plot function is the one that we are using from the BigFish library. It makes our plotting a lot easier compared to matplotlib. Although you can write your own matplotlib based function up here and then keep calling it. But why do that if these guys already provided an excellent way of plotting it? So here, I'm providing what slice I want to see for RNA, for DAPI, and then titles and what frame size I want to define here. So there you go. On the left-hand side, you have the RNA image. On the right-hand side, you have the DAPI image. Obviously, this image can be used to segment the nuclei, and the left-hand side image needs to be enhanced a little bit because it's not really clear, but we can enhance it to enhance these, to make these spots pop up. And more importantly, to also get some sort of an outline for each of these cells, so we can segment these cells as 2 different separate cells. Okay, but it gives a good understanding of what we're dealing with. Okay, let's look at a few processing. I just mentioned about processing this data, these images. So there are multiple ways of processing, and I'll just go through a few of these. First thing first, you can normalize and filter. So let's go ahead and print this. So one slice, the shape is 650 by 500, unsigned integer 16, and Z slice 650 by 500, unsigned integer 16. We know what that is. I just defined a single slice because it makes it easy for us to demonstrate how pixel intensities can be rescaled and all that. This is for demonstration purposes only. So you can see I am rescaling it. So stack offers a method of rescaling, and channel to stretch is none. I'm not stretching it, but if you stretch, then you can say your channel to stretch is 0. If it's a multi-channel image, you can say, hey, use channel number 0, channel number 1, channel number 2, which channel you would like to stretch or rescale. So now let's go ahead and plot our images. I'm going to plot my RNA 2D scaled, where we are not stretching it, RNA 2D scaled and stretched right there. So these are the 3 images. So you can see how things actually pop up once you actually stretch, once you rescale them. So there you go. That's our original image. This is just a rescaled image, and this is a stretched image. So you can see how various things are popping up. Now I can use this stretched image to actually do cell segmentation. I can kind of outline the cell right there, outline the cell right here, right? So these are some functions. You can also have another way of actually getting something similar to this is performing a 2-dimension projections. So you have a 3D stack of 23 images. What if you actually take some sort of a projection? For example, maximum intensity projection is one thing. So in this direction, in the Z direction, get all the only the pixel that has the maximum intensity. So that way you're picking, hand picking the pixels with highest intensity in a specific slice, in each of these slices in that dimension. So that's what maximum intensity is. This is such a common process. I'm pretty sure most of you know exactly what this is. And the way to use it as part of your BigFish library is, again, we keep calling this stack quite a bit. So stack.maximum projection is what we are looking for. And DAPI and RNA, let's go ahead and do that. And let's do exactly the same. Go ahead and plot them. In this case, I'm plotting the fish channel image and the fish channel maximum intensity projection right here. Okay, so this is the original, and this is the maximum intensity. Now you can see these look like the stars in a nebula. So now we can easily segment them or identify these spots right here. Okay. Now, with this information, let's go down. And of course, I gave a couple other examples. If you want, you can do focus projection. One way, this is a good way of actually dealing with out of focus Z slices, where you're actually doing a focus projection. And again, let's go ahead and plot for the sake of completeness so you understand like various projections. I personally choose maximum intensity almost all the time, but just to have a quick look at maximum, the focus channel projection right there. It also gives you similar information, but you see how much cleaner this is compared to the focus projection right there. Okay, so you perform your pre-processing. Let's say we have done our maximum intensity projection. And now we have an image that can be used to perform cell segmentation, to perform spot detection, and we have another image with DAPI channel to actually perform nuclei segmentation. So let's start by segmenting or detecting spots first. So for spot detection, within the BigFish library, we imported detection, and that detection is what we are going to use. And within that, we have a method called detect spots, and we need to provide input image. Again, there are 2 outputs that it actually provides. One is the as spots, the other one is the threshold. So we are going to get both of these, and the image we are going to work with is our RNA image. Of course, you can also work with instead of RNA image, you can actually supply the what did we call this? RNA MIP image. Yeah, either way, it should work, because even here you do have these spots right there. Remember, it looks very faint because this is a 16-bit image, but for the computer, it should actually recognize these. But again, that's an exercise I definitely recommend you to work with. Use RNA MIP and use just an RNA image and see, okay, how does the spot detection get affected? If you want the faintest of the faint spots to be detected, maybe you need to do work with MIP, maximum intensity projected image. But in this case, I'm just using my RNA. And return threshold. Yes, of course, return the threshold. So we know what the threshold value is and what the voxel size is. Now, in this specific case, this image, the voxel size is the pixel size is 103 by 103 in X and Y, and in Z the pixel size is 300. So together our voxel size is 300 by 103 by 103 nanometers, and the spot radius 50 extra pixels in Z. So we are just, and 50 extra pixels in X. So we are just putting a spot radius around each of these to detect our spots, slightly larger than the voxel size itself. Okay, so let's go ahead and do that. In this case, it kind of prints our detected spots. We have 771 of these spots detected right there. Now we can go ahead and plot it. Again, plot detection is a function that is part of plot, which means you have to provide the input image on which you want to apply or draw the spots, and the spots itself. So it knows where to draw these spots. Yeah, so there you go. So that's your input image, and this is where all the spots are detected. And here, if you see that some of the faint spots are not being detected, like in this case, it actually did a pretty good job. If you think that some of these faint spots are actual real spots, this is where I would go back and change my input image to maximum intensity projection and then perform a spot detection on it. Remember, I'm overlaying this circles onto my maximum intensity projected image right here, but then the spot detection itself was done on the actual RNA image and not just the MIP, maximum intensity projected image. Okay, so this is where you need to play and see which one works for you. Now you can also look at the automated spot detection. It actually tries to find this optimal threshold to discriminate between the spots or noisy blobs. Like there is, I mean, at some point you're saying, hey, this is noise, this is a spot, right? And this is a threshold that gets automatically defined in the way that we have done, but you can define your own threshold. But if you want to see where the threshold is actually performed, you can actually plot these breaking points, like by changing the threshold, what is the number of RNAs detected as a log scale. And typically we pick the elbow, right? So this elbow is what the system automatically selected, and that is the threshold. But yeah, just a visualization of where the threshold actually got obtained here. Okay, so now what we have so far are the spots detected, but if you look at some of these dense regions, you see this dense region, right? This dense region, that may be a combination of multiple spots together. So you can actually perform a decomposition of that dense spot into individual spots, and that's exactly what the next step is. So we are decomposing the dense, and we provide our RNA, your input image. Again, RNA or RNA maximum intensity projected, it's up to you, and the spots itself, and the voxel size, spot radius, and there is a parameter called alpha, beta, and gamma, and they impact the number of spots per candidate region. So again, this is something where you play with to fine tune it to your liking. And yeah, let's go ahead and decompose this, and what we get out of this is, of course, the spots decomposed and the dense regions that we can plot onto our actual image itself. So now, instead of plotting only the spots, now let's plot the spots decomposition. So it gives you the new set of spots that actually gets overlaid onto your input image. And here you go. And now you can see how it decomposed these regions into various individual spots. I hope you can see that on your side. It looks like a whole bunch of these rings on top of each other, which they are, and that's why these are basically nothing but decomposed, and you can see some of those right there. Okay, now you can actually detect the clusters once you decompose them. Obviously these are clusters, right? So let's detect like clusters. Where are the spots agglomerated? Of course from this dense region, but also everywhere else. So the next step is the cluster detection. This is a typical process: spot detection, decomposition, cluster detection. And again, very similar process right here for cluster detection. Within the detection, you have detect clusters, and everything else is self-explanatory. Let's go ahead and do that and print out how many clusters do we have. So spots, after clustering, these many spots are detected, and clusters, 21 clusters are detected. Again, you can plot those, plot detection, and you can actually put the clusters on top of the spots itself after decomposition. And for the clusters, let's actually use a polygon with blue shape and a radius of 6 and a line width of 2. Change all of these if you like other colors and other way of displaying on your images, displaying these regions. Okay, so there you go, and you have all the spots, and wherever you have these clusters, you have this polygon shaped filled with blue. That's a cluster right there, right in the middle. So we have multiple such clusters. Again, that's another useful piece of information. And now let's, if you want, again optional, you can actually perform subpixel fitting, because now we're talking about refining these spots that are already detected down to a subpixel level if the accuracy is more important to you. And again, you define your own threshold there, and this is the threshold we previously got from our automatic way of finding the threshold, but you can define a different threshold if you want. And so basically here what we are doing is detecting the spots, and once the spots are detected, I am feeding that as an input to the next function, which is fit subpixel. It's going to do a subpixel fitting, again using the parameters that we defined down here. Usually these are the steps that you do one after the other, so that's why I'm redoing this spots step. So we combine them at one place here. And once this is done, we will go ahead and do the plotting, and now you can see with just the spot detection, we got 771 spots. We saw the same number earlier, and now it's actually performing subpixel fitting, which is obviously slower compared to the spot detection itself. Yeah, so now it's actually done with its subpixel fitting, and now we have 771 spots right there. Let's go ahead and plot them, spots and subpixel spots, and I think we should see pretty much the same thing. Maybe we'll see some red because we are overlaying blue on top of red, but you can see some, after subpixel fitting, some of these are slightly moved to the side. As you can see, there is some shadow or some leftover region of this red, but it's just a way of improving your pixel fitting down to a subpixel level. Okay, so now we are happy with one of these methods. Maybe I'm just taking my subpixel fitting, and this is the data. These are the spots that I'm working with. Okay, after this step, and what do we do next? Well, if you have multiple signals, multiplexed data set, where you have 3, 4, 5 different channels showing different information, then you can think of actually performing some sort of co-localization and continuing. But again, I'm just giving this for the sake of completeness because the documentation actually provided this example. I want to make sure some of you who relate to this, at least have access to this, but I commented that part of code. Let's go down and look at the next step, which is basically we have all the data until now, which is our spots information. So we can actually save them as NumPy files if you want, or we can save them as CSV. CSV is what we will be importing in the later step. Of course, you don't even need to save any of this. You can just directly go to the segmenting nuclei cells and analyzing, which is what we'll do in the next file that I'm going to show in a few minutes. But again, for the sake of completeness, let's look at how you can save this data. You can save your spots and cluster information as NumPy arrays or CSV. We save them as both in our output directory. And now let's go ahead and move on to segmenting the nuclei and segmenting our cells. Well, there are various ways of segmenting nuclei and cells. And first thing first, let's first have another look at our DAPI and RNA channel so you can see exactly what we are dealing with. So here is our DAPI channel, and this is our slice number 11 that I'm actually showing. And this is the RNA channel, same slice. So we know that, okay, we can perform cellular segmentation here and nuclear segmentation using DAPI. At least there we have clarity, right? I definitely recommend using CellPose, which is a deep learning based segmentation for cellular segmentation, and using Stardist, which is again a deep learning based model that works great in most cases. I should say not all the time, in most cases for segmenting nuclei. But this is such an easy case scenario. Let's not bother installing that library, but we need to install CellPose library for cell segmentation. That's exactly what we are doing right here. It's very simple and easy. Access to deep learning actually. So we are just going to install cellpose, and once it's done, it's literally 2-3 lines of code for us to segment these cells. Okay, I think that's done. So now let's go ahead and import from cellpose, import core and models. And the model that we're going to use is called a situ model type, and GPU equals to true because I am using a runtime of GPU right here just to make segmentation faster. But in this case, I only have 2 cells, so it's a bit of an overkill. But still, for deep learning, I always try to enable GPU. Okay, the first time it downloads the model. That's not that bad. It's pretty fast. And now the model is ready. Let's go ahead and define our channel. And grayscale, we are working with a grayscale image, right? We are working with individual channels. It's not an RGB. It's not like a histology image where it is color. So I'm defining 0 and 0. For RGB channels, you need to define something else. And again, look at cellpose documentation for that. But let's define channels, and that goes in as an input as part of your model.eval. When you do model.eval, it is like model.predict. It's you're doing the segmentation, and on a specific slice. Again, you can use a MIP image, maximum intensity projected image. In this case, I'm using a specific slice number and provide what the approximate diameter is of the objects and what batch size you want to work with. So let's go ahead and run this, and it provides 4 outputs. All we care about is cell label. That's exactly what I'm getting here. And if you look at the plot of this, there you go. This is the plot. This is the input image. This is the cellular segmentation that we have. So we have 2 cells. I'm happy with this. And let's go ahead and continue. And of course, you can also define the plot, the segment boundary, which, as the name suggests, it just shows you the boundary of this segmentation. There you go. Okay. So far, so good. Now let's do nuclei segmentation. This is where you can try, again, fancy ones like Stardust or something else, but let's just go ahead and use the ones that are available as part of bigfish.segmentation. And this also uses TensorFlow in the backend. It requires TensorFlow add-ons. So let's go ahead and install that. And once that's done, we are going to import the segmentation from bigfish.segmentation and then perform a unit-based segmentation. Again, this is also deep learning. I could have just done thresholding, but this is a cool way of segmenting images. So there you go, segmentation.unit 3-class nuclei, and it prints out the summary in a second, so we can have a quick look at what the model looks like. Yeah. And as you can see here, whatever the input shape is and output shape is, and these many parameters. So this is basically a unit model. And now that you have your 3 classes model, I mean, that's why the output is 3 over there. Now we can go ahead and apply that unit 3 classes, right? I mean, we defined a model called model_nucleus or NUC, and we are going to apply that model_NUC onto our DAPI image on the 11th slice with a target size of 256, because these models, you need to define a specific input shape and so on. So that's what we're defining right there. And test time augmentation equals to true and all that stuff. Let's not get into the deep learning aspect of it. You can use these lines as is, and we should get a decent segmentation, I hope. Okay, let's go ahead and plot it. There you go. So we have 2 nuclei, very well segmented, nicely segmented, and we are all set. And this is more dramatic when you have a whole bunch of nuclei, a whole bunch of cells. But in this example, we only have 2. Great. And now let's perform post-processing. You can perform some cleaning steps. For example, the cell label. Let's go ahead and get that image. And you can just do some sort of a cleaning the segmentation, like smoothing it. And sometimes you may end up with some of these individual like pixels here and there, or some jagged edges around your cells. But this is, again, clean segmentation kind of takes care of all of that. And clean segmentation, let's go ahead and perform that on our nuclei labels and cell labels, meaning the segmented nuclei and segmented cells. And let's go ahead and run these lines and plot it after it's done. And there you go. So this is our nuclei segmentation after the cleanup, and this is nuclei on the left hand side, cell on the right hand side. Again, go ahead and compare them with before and after, but again, this is a walkthrough of all the functions that you have available at your disposal. So you can pick the one that works well or that you like, for your data set. Okay, now save the results. Again, if you are doing only the pre-processing and all of that, go ahead and save it into your, wherever you want to save them. So now we have two TIFF files that we saved. Nuclei labels and cell labels. Again, there's no need for you to save any of this. You can put everything into one long workflow and just focus on the results, which is what I'll show you in a minute after we go through this process. Now, once you have this, now let's start extracting the cell level results. So how do we extract the spot, the spot data at a cell level? Now, let's go ahead and print this information for now. So we have a DAPI channel of 650 by 500, 23 in Z. And we have a smFISH channel, a single channel, same size, of course. And now we also have the spots that we detected saved as NumPy array or CSV. We also have the segmentation of these saved as TIFF files. So with that information, let's bring everything together. That's exactly what we are trying to do. And here we are trying to generate a contrasted image. So it makes it easy for us to visualize and segment and overlay. So this is basically, again, we are rescaling it. We saw this earlier, right? And where we added a bit of a stretch right there. And on that scaled image, we are performing maximum projection. Again, this is only for visualization purposes, optional step. And let's go ahead and run this so you can see exactly how this looks like. So there you go. That's the original, and this is the final image that I'm talking about, which looks a bit contrasty and stretched. Yeah. Okay, next step. Now read the segmentation and detection results. This is only because we saved the results and we are reading. Otherwise, they're available for us in this notebook anyway. So all I'm doing is just reading my segmented cell, segmented nuclei, all the spots that we just detected, and saved as a CSV file. So I'm just reading a CSV file right there and the detected foci points right there. Yeah, but I'm reading all of these, which is basically the clusters. Yeah, so I'm reading the clusters, I'm reading the spots, I'm reading our labeled image, and I'm for both cells and nuclei, and they're all available to us. And now let's go ahead and perform the actual analysis that these guys make available via this transcript sites function. Transcription sites, remove transcription sites. You can go through this, but if you want me to read this and bore you, a transcription site refers to the location in the nucleus, right? Inside the nucleus where RNA is being actively transcribed from DNA. And in FISH analysis, this is a cluster inside, detected inside the nucleus. Typically, that's what it's clustered. So basically, all that is doing is, hey, remove any clusters you find within nucleus. That's what that basically means. And again, please go ahead and read what foci are, what transcription sites are. Again, I'm going to share this document with you, but we are going to perform this remove transcription sites operation. So after this, we get two things, right? Spots with no transcription sites, foci, and the transcription sites. And what do we do that? Now we can identify objects in specific compartments. Now, identify objects in region is what it does, and you can use the spots as your input right there and nuclei label. And let's go ahead and perform this task. And again, once everything comes together, it makes sense when you put this onto a visual image. So now we have spots in and spots out. In and out of what? Of your nuclei right there. Basically, that's what we are trying to achieve in this case. So inside the nuclei, you have 360 spots of all the 1100 something, right? 1129 spots. And outside the nuclei, you have 803 spots that are detected. Okay, now what? Now from nuclei, go to the cellular level. Okay, so extract cell, and you provide your labeled image right there, and you provide your nuclei labeled image, and you provide your spots. In this case, we chose to not include the transcription site spots, and that's what we're providing here. And any other coordinates you want to plot, for example, foci, transcription sites, and if you want the image to be included, I'm providing image contrasted, so everything will be placed on that image. You can use any of your input images. That's not a big deal right here. And other images you can go ahead and provide. So number of cells identified 2, obviously we know that there are 2 cells. And for each of these cells, if you have thousands of cells, this would be amazing. For each of your cells, go ahead and do the following actions. And basically we are just plotting them as you will see in a second, right there. So we are plotting these spots that we identified up here. We are plotting every one of these: nuclei mask, cell coordinates, cell mask, and RNA coordinates, foci, and the transcription site coordinates and contrasted image is what we are using in the background right there. So use all of these and plot them, and on the left hand side you can clearly see that it is overlaid onto our image that we have chosen. On the right hand side, it's just a sketch of where the nucleus is, where the cell is, and where different types of regions we have, and these are clusters that are numbered right here that you see here. Yeah, and remember, we removed these from inside the nucleus, so you don't see any of those from inside the nucleus. Okay, so that is, and for each cell we are printing it. So this is for cell number 1, this is for cell number 2, the same type of information. Well, visualization is one thing, but capturing that as a data frame and saving it as a CSV is very useful. That's exactly what we are doing here. Summarize extraction results and save it as a pandas data frame. And this gets stored as part of a pandas data frame. And if you just look at, we only have 2 cells. That's why we have 2 rows here. And there is the information about the cellular area, nuclei area, and how many nucleus RNA you have, and how many outside, and so on. So you have all the information down here, how many transcription sites, and you can save that as part of a CSV file or a a NumPy file in this case. So there you go. And again, you can just go ahead and load the one that we just saved and print the results, so you know that, hey, this is the type of information that got saved. And a lot of information, including ID, bounding box, like where the cell is, the coordinates of the bounding box of each of these cell coordinates, cell mask, and everything is saved right there. And for each cell, you can compute different features. For example, you can actually, basically, it's how far is this RNA from the, from within the nuclei, and so on, right? I mean, there are a bunch of features that you can actually print, and that is exactly what we are trying to do right now. Load the single cell data that we just saved. Again, we keep saving and loading, but I'll show you, like I promise, I'll put all of this into a single function, so we don't need to worry about all this saving and loading. All of this just so you know exactly how to work with this. Yeah, once we load all of this, now we are going to import a function called classification within bigfish.classification, and that offers various functions. I mean, that offers like various features, I should say. And let's go ahead and get the feature names. So when you get feature name, there are various features that you can actually extract. One is distance-based, and then intranuclear features, there is protrusion features, there's dispersion features, there are topography features. All of those are available as part of this get features right there. And just for feature names 1, these are the metrics that are our features that are part of this distance, which is mean distance from the cell, median distance, mean distance in nuclei, and median distance in nuclei. Similarly, go ahead and look at intranuclear and all that other features, but this is just looking at it. What good is looking at it? We need to compute them. So to compute and capture them as a pandas data frame, let's go ahead and import pandas. I think we already imported that, but that's okay. And we save this as for each cell, we save the NumPy array, right? That's what we printed up here. For each cell, up here. For each cell, we save the NumPy array. Cell 0, cell 1, cell 2, cell 3. And now we are just importing that NumPy array here. Again, we are doing a lot of things twice. But for each of these NumPy array, go ahead and do the following, which is compute features and compute the whatever the features that you are defining down here. Like, do you want to do distance? Do you want to do intranuclear? Blah, blah, blah. All of that, there is a whole bunch of stuff. And we are going to capture all of that into a pandas data frame. And we are going to print the top few rows. Of course, we only have 2 rows right there. And now you can see mean distance, median distance, mean distance from nuclei, median distance, and all the information that you have. It's not so cool with only 2 cells. I wish I had a data set that's got like a whole bunch of cells and nuclei, and this would be such a fun exercise then. Well, once you have that, you can save this as a CSV file. I hope you appreciate the Big Fish library for this type of smFISH analysis, and I added some extra end notes. But before ending this video, I really would like to take a few more, 5 more minutes or so to show you another example. Now I switch this. So let me runtime disconnect and delete runtime of the previous one, and that's because I'm using the free version and I can only use one runtime at a time because I'm using GPU. So let's switch this, and now it's initializing. Okay, so this one is basically multiplex. Yeah, in this data set, I mean, I actually downloaded this. I did a Google search of where can I get these type of data sets, and I actually found one. Luckily, it's a CZI image. That's a Carl Zeiss microscope image where you have a single image, CZI, that has multiple channels, and it's a 14 Z slices, each 201 by 201 pixels, and it has 4 channels: CY5, DS-Red, EGFP, and DAPI. Obviously, DAPI, we are going to use it for nuclei segmentation, and in this specific order. Yeah, right there. And the scaling is 31 microns by 31 microns by 40 microns. I think I should move 40 to the front because 40 microns, 310 nanometers by 310 nanometers by 400 nanometers in, and the 400 nanometers is probably in Z, so I should have moved that to the front. But anyway, these are the details about the data set. Everything else remains the same. Okay, with that information, let's go ahead. Let's install the Big Fish. Let's install CZI file library. This is a different notebook, so I'm installing all of these, but I promise this to be a fast journey. And CZI file is a library that you need if you want to work with CZI files in Python. So let me install the CZI. If you're working with SVS, if you're working with Olympus, whatever, install the appropriate library so you can read those images. And I am going to install Stardust because I want to show you how amazing Stardust is at segmenting these nuclei. So we have multiple nuclei here, so I may as well show you the Stardust example. So I'm installing Stardust right here. So once that's done, we are ready for business. So I'm importing all the libraries, exactly the same ones we imported before, in addition to that CZI file, so we can read the image, and in addition to that Stardust, so we can segment the nuclei. And I'm importing something called Stardust 2D. Yeah, I'll get to that in a second when we get to Stardust. Now, the first thing that now I put everything into a couple of functions. One is segment nuclei. Obviously, the goal is to segment nuclei, and the input is going to be a DAPI image, right? And what does it do? Well, first, our DAPI image has, in this example, like 14 slices, right? Our input image is a Z-stack. We need to collapse that, or we need to pick one slice, or we need to collapse that into a maximum intensity projection. I should have used only MIP in my last example, but that's we're correcting that here. So first thing first, it's going to perform a maximum projection on the DAPI image. So we end up with a 2D image. Remember, this is a 2D image now. And that 2D image is going to be the one that we are going to segment, but using what model? Within Stardust, you have a few trained models. I think 3 pre-trained models. I'm going to use the one that's called 2D versatile fluorescent model, and that's the one that's appropriate in our case. There is also one for, I think, H&D images if you're working with those, but obviously we're talking about fluorescence images right now. So, okay, so 2D, that's the model. And using this, I am going to segment using model.predict instances and this. And of course, our input needs to be normalized because that's how the model got trained on. And then what we get out of this is 2 things. The maximum intensity projection image, I want to return it, so we can use it as part of the next step, and also the nuclei labels. That's it. So let's go ahead and run this function. And the next one is something that you saw in the early part of this presentation, right? So we provide an input image or input channel. In our case, we have multiple channels, and the voxel size, because voxel size is an input that we provide when we do spot detections and decomposing these and so on. So that is important. And spot radius, like what radius do we want to provide, right? So these are the inputs that I'm providing to this function, but then it does pretty much what we have done until now, which is calculate the maximum intensity projection, and then perform the detect spots, spot detection, and then decompose the dense regions, and then perform clustering. We did all of this for the first 30 minutes or so. And once you do that, then go ahead and segment the new DAPI image. yeah, right there, and then perform your transcription, remove transcription sites from within the nucleus. Unfortunately, in this image, which we'll see in a minute, we don't have a channel that we can work with to segment cells. We only have nuclei segmentation, but we are going to call them cells. This is absolutely not the right thing to do, obviously, but in this case, when I say extract cell, I'm going to extract nucleus, not the cell, because we don't have cell segmentation. But that's something you need to add here, segment cells. Yeah, another function to segment cells, and then add it here. In this case, we don't have that. And then rest of the stuff is pretty much straightforward. For each of these results, go ahead and report these and then capture them as a pandas data frame. So that's what this function actually does. Now let's go down and look at the input image. Our input image is called mouse1.czi, and channel number 0 is sci-fi, channel number 1 is red, channel number 2 is our GFP, and the last channel is our DAPI image. And our voxel size is 400, remember 400 nanometers by 310 by 310. And the spot radius I want to use is 50 plus that. I'm adding 50 pixels to each of these. So that is the input information. And let's go ahead and quickly visualize this entire thing is useless for our purposes in general, because we want to automate it so we don't even have to look at the image. But for now, let's get a quick idea of how our images look like. So let's go ahead and, by the way, we're performing nuclei segmentation, so we can also have a quick look at it. But once this is done, let's have a look at all of these images so we have a good idea of what we're dealing with. Okay, so there you go. That is the sci-fi maximum intensity projected image. That's the red, that's the GFP channel, and this is our DAPI channel, and this is the segmented DAPI. This is real life scenario, right? Now you have a bit of more complicated scenario, but again, we don't have a channel that we can use to segment cells. We only have nuclei in this case. That's what I mean. Now, hopefully it makes sense to you. Okay, now we just need to process channel. What is that process channel? That's that function that we defined up here. This one, this entire thing is process channel. When you do that, it gives you numbers at the end. That's it. As simple as that. This is a real way of actually working with this data. So let's go ahead and process it 3 times. One for sci-fi, one for DS-Red, one for GFP. It's pretty fast. It's all nice and automated. And now what we are doing, now that we have data frames, 3 different data frames, right? We have one for sci-fi, one for DS-Red, one for GFP. I'm just combining all of those into single. That's exactly what we are doing down here. And actually adding extra column at the end where I add a column called channel and then basically record whether it came from sci-fi or DS-Red or GFP. That's it. Hopefully you'll see that when you look at the output. I saved everything into a CSV file, but let's go ahead and look at some random. .sample basically means show me some random data points, and this is how it looks like. Cell ID, cell area, nuclei area. In our case, cell equals to nucleus, so it's the same number. And how many RNA and what channel did we use right there. So in cell number 13 for GFP channel, we have 3 RNA. I hope that makes sense. We may have sci-fi, we may have GFP, and so on. For that, I think it makes more sense to do that, of course, analysis, but plotting definitely helps. And I'm just giving you, since I'm sharing the code, I'm just giving you a few plots that you may find useful. And of course, you can customize this for your specific use cases. Now here, let's do a total number of RNA in each channel. In sci-fi, we have like over 200 RNA total, combined all nuclei. And DS-Red and GFP fewer compared to these two. And the other one you can look at is compare the distribution of this RNA across different channels. And again, this is a good relevant way, same information, but looking in a different, using a different plot. And again, same information using violin plots, because I personally like these. So it kind of tells me what the distribution looks like for these RNA counts. And scatter plot also helps you. Now here we are looking at the relationship between the nucleus area and RNA count. In a way, I'm like, okay, do I get more nuclei, more RNA if the nucleus size is larger? So that's the type of information that you can, again, extract from this data. And you can also look at the distribution of RNA counts within each channel. So again, all of these combined will give you very good idea of what's going on with your sample. But again, this data set is not as good as I would love it to be. Again, heat maps is such a common thing to do in this type of analysis. It'd be a shame if I don't include it. That's why I included that, so you can kind of clearly see cell number 12 has a lot of these spots. Of course, that's one of the big ones, I guess. So there you go, a few plots using this data set. So I hope, again, I appreciate you still sticking around, because it's, I guess, almost an hour into this presentation and you're still around. I appreciate that, and I hope you found this tutorial to be useful. And again, as usual, I request you to hit the subscribe button, and let's meet again in the next tutorial.